Okay, good morning, everyone. I keep saying that. I'm usually doing these in the mornings. We're going to talk about calorimetry now, okay? Um, we talked the other day about enthalpy and the concept there and how that's related to heat, okay? And so the idea here is... It's not moving very well. Okay. The idea here on heat, again, is that heat and enthalpy are essentially the same thing at constant pressure, okay? Now, they're not exactly the same thing when we're not at constant pressure, which we're going to talk about a little bit at the end here. But for the most part, in this class, you're just going to assume we're in a constant pressure situation, okay? So what that means is delta H, right here, delta H stands for heat flow or heat change throughout the reaction, okay? And we cannot know exactly what the H is at any given time. It's just too difficult. Again, we talked about H is related to internal energy, and it's really, really difficult to know the exact amount of internal energy that's going on in a system at any given time, okay? But what we can measure, we can actually come up with a way to use temperature change to figure out what our heat change is, or the change in energy that we have, okay? And so we can actually relate those two to one another. And that makes it a little bit easier, a little more manageable, because then we can actually do an experiment where we measure the temperature change of, a lot of times we use water, and we can figure out exactly how much heat is flowing from one place to another during a chemical reaction, okay? Alright, so we know a couple things about substances that help us to identify those substances. It's sort of like density, in a sense. But the amount of energy that it takes to raise the temperature of substance by 1 Kelvin or 1 degree Celsius is called its heat capacity, okay? Now, different objects have different heat capacities, just depending on the way that their molecules interact. Some things, it takes a lot more energy to raise their temperature by 1 degree than others. And you guys are familiar with this concept, even if you're not aware that you're familiar with it. Anytime you boil water, you're working with two different things that have two very different heat capacities. So you've got the metal, which heats up very quickly. You don't have to, provide a lot of energy to that metal to change the temperature of it by quite a bit. And that's why we use it for cooking, because they heat up fairly quickly. The water that's inside that metal pan, or metal pot, whatever you're doing there, that water has a high heat capacity. Okay, it takes a lot of heat to heat that water up, from 0 to, well, not from 0 probably, but from 20 degrees Celsius to 100 degrees Celsius. It takes a lot of energy to do that. Okay, so water has a higher heat capacity than that metal. So it's unique for every object. Now, sorry, something's looking up on me here. I really need it not to do that this morning. Okay, here we go. So, specific heat capacity, there's only one difference here. It's the amount of energy it takes to raise 1 gram of a substance by 1 degree. Come on. Okay, it's the energy that it takes to raise 1 gram of a substance by 1 Kelvin or 1 degree Celsius. Okay, so same basic thing there. Boy, this is gonna really be annoying. Okay, so when we're talking about specific heat here, the formula for specific heat, and the book uses S for specific heat, but on your equation sheet, which you get to use for this test, it's actually C, okay? So I wanted you to see the actual unit that we're using here, okay? To find the specific heat of an object, you need to take the heat transferred in a chemical reaction divided by the mass times the temperature change, okay? So C equals Q. Q is heat. Delta H is also heat, but in these reactions we use Q because sometimes they're not done at constant pressure. Divided by M times delta T. M is mass, delta T is the temperature change, okay? That's how you find the specific heat. Now, if you rearrange this equation, actually we'll get to that in a minute, so I'll hold off on that. Okay. Well, we'll talk about it right here. So sample problem, how much heat is needed to warm 250 grams of water from 22 degrees Celsius to 98 degrees Celsius? Okay, and the specific heat of water is 4.18 joules per gram times, this is supposed to be the times sign here, times Kelvin. Okay, now, this unit right here could also be written as joules per grams times degrees Celsius because we're talking about temperature change here, okay? And the amount of change you're going to have in Celsius or Kelvin is going to be the same because a change of 1 Kelvin is also a change of 1 degree Celsius, all right? So we don't have to worry about converting these temperatures into Kelvin. They can stay in Celsius. Now, they obviously couldn't be in Fahrenheit. We need to convert it if they were given to us in Fahrenheit, but they never will be, so. Alright, so we've got our equation here, C equals Q over M times delta T. But what they're asking us for here is they're asking us how much heat, okay? And so that's Q. They're asking us for the Q here. So if we rearrange this equation, we get Q equals C times M times delta T, okay? And so then we just have to plug everything in here. It says the specific heat of water. You've got to differentiate between specific heat and heat, okay? Heat is however much you are adding to the substance at that particular time, okay? Specific heat is, that's an internal quality of something where it's how much heat you have to add to something to raise it by 1 degree Celsius, or 1 degree Kelvin, okay? So that's the difference between those two. The heat is going to be different for every problem that you work. The specific heat of water is always going to be 4.18 joules per gram degree Celsius. Okay? Alright, so we've got 4.18 here. And I'll put my units in just so we can see how these cancel one another. Joules per gram. And I'm going to do times degrees Celsius because that's what our temperature is given to us in. Times our mass, which is 250 grams. Now notice that's going to cancel out the grams in the specific heat number times the temperature change. So it's going from 22 up to 98. Okay, so that's going to be a temperature change of 76 degrees Celsius. Okay, grams cancels out, degrees Celsius cancels out, and we multiply these together. This is going to give us our heat in joules. Okay, so can we work this out? 79,000. Let's match our sig figs here. Really, it's 79,000 because there's only 2 sig figs on most of these numbers. So 79,000 joules. That's a big number, so we could report this number in kilojoules. It would be 79 kilojoules. It doesn't specify on this problem, so whichever way you want to report it is fine. Okay. A lot of times these heats will be reported in kilojoules because the joule number is fairly large. Okay. Next, what is the molar heat capacity of water? Okay. So we just talked about the specific heat capacity, which is 4.18 joules per gram degree Celsius. Okay. I'm trying to go back. Come on. Sorry, this really is annoying. Okay, you know what? I don't need to go back. I can't remember the number that we just did. We just found 79 kilojoules of heat, okay? Now the molar heat capacity, that just means kilojoules per mole or joules per mole, whichever one you want to do, okay? So it took 79, there were 79 kilojoules of heat given off here. And how many moles of water did we have? I think it was 250 grams of water. Oh, this thing is really locked up on me now. Here we go. Okay. So 250 grams of water. And it took 79 kilojoules of energy to raise it that amount. Okay? And so molar heat capacity, they're just wanting kilojoules per mole. So if we have 250 grams of water, we just have to figure out how many moles of water that we have. Okay, 50 grams of H2O. Change that to moles of H2O. 18 grams. They're not usually going to ask you for the molar heat capacity, but that's what that basically means. Is they want kilojoules per mole is what they're asking you for on that one. Okay. So this is going to be, let's see, 250 divided by 18, 13.9 moles of water. Okay, so then we divide that by 13.9 moles. That's going to give us about 5.7 kilojoules per mole as the molar heat capacity of water. Okay. And again, most of the questions I've seen on the AP exam, they're going to be more obvious with what exactly they want there. But that's what molar heat capacity is, because the regular heat capacity or specific heat capacity deals with grams. Molar heat capacity. Excuse me, sorry, it's too early in the morning for this. Molar heat capacity is going to be in moles. Come on, PowerPoint. So, how are you guys doing today? There we go. Okay. Constant pressure calorimeter. This is our typical calorimetry that we're going to do. The lab that we do in here is going to be a constant pressure calorimeter. Okay, and these things are really fancy. 2 styrofoam cups put together with a stopper on top. Sometimes you don't even use a stopper on top, and a thermometer stuck into it. Okay. And you add 2 things that are going to do a chemical reaction, and you basically you can measure the heat change for that system by measuring the heat change for the water. So if you know the initial temperature of the water, and then you know the final temperatures after you've mixed them together, you can figure out your temperature change, and you can actually figure out the heat flow that's happening in the reaction. Okay. So again, not a very complicated setup, but this one's done at constant pressure. Okay, the gases are allowed to go outside or inside based on what they need to do. Okay, so this is not an airtight type of thing. So that means that Q is equal to delta H on these types of calorimetry problems. Okay. So we know the specific heat for water. Okay, we already used that. It's joules per mole times Kelvin. Then we can measure the delta H for the reaction with this equation, Q equals M times C times delta T. Okay, and we just used that equation for an example problem. But let's look at another one here. Okay, so let's say we've got, and these things are fancy. They're called coffee cup calorimeters. Okay, those are the ones in the styrofoam cups, and that's actually a scientific, very scientific piece of equipment there. Man, this is just, I don't know why it's so slow this morning. So students mixing 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar NaOH, and the temperature increases from 21 to 27.5. So we want to know the enthalpy change for the reaction. Assuming that the calorimeter loses only a negligible quantity of heat and that the total volume is 100 milliliters, the density is 1 gram per milliliter, and they're giving us the specific heat of the solution. Okay. All right. So first thing that we need to do here is we need to essentially we're figuring out the enthalpy change. Okay. So they're asking us for delta H here. Okay, which is the same thing as Q in a constant pressure situation like the coffee cup calorimeter. Okay, so this is C times M times delta T. All right, so we got to figure out our specific heat, we got to figure out our mass here, and we got to figure out our change in temperature. So what we have here is 50 milliliters of a 1 molar HCl and 50 milliliters of 1 molar NaOH. Okay, and we don't need to know milliliters, we don't need to know volume, we need to know grams. Okay, but we're going to assume here it says the density is 1.0 grams per milliliter. Okay, so we mix these two things together, and what we're going to end up with is 100 grams total, right? So because this right here is 50 grams of the HCl, and right here this is 50 grams of the NaOH, okay? Because it's 50 milliliters of it. Let's see here. So then, I'm sorry, hang on just 1 second. Of course, it's going to take forever to pause this thing now. I apologize. Okay. I'll come back to this in just a second. Let me... Okay, sorry about that. I need to go back for a second because as I was going through this problem, I was still thinking about the last one that I showed you, the molar heat capacity of water. Still moving slow, awesome. So the molar heat capacity of water, that actually includes a temperature element to it as well, and I'd forgotten that, so I apologize. Sort of back up, forget what I said before. We know the specific heat capacity of water is 4.18 joules per gram times Kelvin, okay? Basically, we just need to find the molar heat capacity. This grams needs to be in moles instead of grams, okay? So to get that into moles, grams is on the bottom of this number right here. So we need to put 18 grams on the top, 1 mole on the bottom, okay? Then grams is going to cancel out, and then we'll end up with here's my calculator. Just had it. There we go. So then we'll end up with 4.18 times 18, 75.2. Really, probably just 75 joules per mole times Kelvin. Okay, so there's a Kelvin component there. It's not just joules or kilojoules per mole. You also have to include the temperature in there. Okay, so that's the molar heat capacity of water. Sorry about that. Well, it's moving a little faster now. I spoke too soon. Okay, now coming back to this problem. Sorry about that. Let's see, where were we on this one? Okay, so we were talking about the fact that this 50 milliliters right here, because the density is 1, this is also 50 grams. This right here, 50 milliliters, so this is 50 grams. So total, our mass of our solution is 100 grams, okay? So if we're finding the delta H of this thing, and our specific heat is 4.18 joules per gram times Kelvin times 100 grams times our temperature change, our delta T. And so our temperature change here is, let's see, 5.5. Is that right? No, 6.5. Okay, so it's going up 6.5 degrees Celsius, or Kelvin, okay, either way, because it's basically the same thing. So then when we multiply all those together, we have 4.18 times 100 times 6.5. 2717, and with our sig figs here, well, a couple of these are 1 sig fig, so let's just say 2700 here, and that's joules, okay, and that's our delta H. Now, here's where we have to be careful. With delta H, the sign matters, okay? We need to think about what's going on in this reaction. It's going from 21 to 27.5, so it's warming up. In other words, when you put a thermometer in there, it is releasing heat into the thermometer. So the reaction itself must be exothermic. It's giving off heat, okay? And an exothermic reaction, the delta H, is negative, okay? I wouldn't worry about the sign until you get to the very end. I think it's less confusing if you just work out the numbers, and then at the end you think about, okay, should this be a negative or a positive number, based on whether it's exothermic or endothermic. But they make a big deal about the sign on the AP exam. You got to get the sign right, okay? All right, next, bomb calorimetry. This is the last thing here. Volume calorimetry is actually a closed system, so the pressure is not well, it's not the gases are not interchangeable with the atmosphere, which means the pressure will change when these things actually they don't explode. It sounds like a bomb, you know, but it's really they're burning something. Okay, and what they do is they have these electrical leads that pass a lot of electricity through. A lot of times it's a piece of food. This is how they figure out how many calories are in your food. That number that they put on the back of the box at the grocery store. This is where they get this number from. Okay, they put this wire in contact with the sample, and they just measure basically how much burning this food changes the temperature of the water inside the bomb calorimeter. Okay, and that's how you can measure this heat. Come on, move. The volume is constant here. Okay, so what that means is the pressure changes, and if we're not at constant pressure, we're not technically measuring delta H anymore. So the Q, the heat here, is not exactly equal to the delta H, but it's actually close enough that we can really approximate here. Okay, there are conversions that they use in order to make sure that they get from Q to delta H. We're not going to worry about those in this class. Okay. So let's do an example of a problem with a bomb calorimeter. And what they basically do here is they figure out how much heat the calorimeter itself is absorbing when the food burns, and then you can figure out the energy in the food. Come on. I'm really sorry about this. This thing would be over by now if this PowerPoint was moving faster. What else can I say here? Okay, difference is small. Thank you for that. Okay, and this was a simulation, but it's not really working at this point, so we'll just go past this. This is basically just showing how you can put different things into this bomb calorimeter and burn them and see the temperature change, and then you can use that to figure out your heat flow. Oh, come on. Okay, here we go. So we've got this this long equation here, okay, this reaction that's happening when you combust methyl hydrazine. And they're saying when you've got 4 grams of it combusting in a bomb calorimeter, the temperature increases from 25 to 39.5. Okay. In a separate experiment, the heat capacity of the calorimeter is measured to be 7.794 kilojoules per degree Celsius. And they want to know what the heat of reaction is for the combustion of 1 mole of the CH6N2. Okay. Now this one, on these types of problems, if you just look at the units in the problem, a lot of times it will make sense. Okay, you don't necessarily even need the Q equals C times M times delta T equation for these. Okay, because what they're telling you is they're telling you the heat capacity of the bomb calorimeter. Okay, in other words, every 7.794 kilojoules you put into this thing changes the temperature of the bomb calorimeter by 1 degree Celsius. Okay, so if we know that and we know the temperature change that happened here, we can figure out the heat change that happened because we've got this unit right here, kilojoules per degree Celsius. Okay, so we've got this 7.794 kilojoules per degree Celsius. Okay, and if we take that and we multiply that by the temperature change that happened, which here is let's see if I can do this. 13.5. No, 14.5. 14.5. Gosh, why am I so bad at this? I just need to double check my math real quick. Yeah, 14.5 degrees Celsius. Okay, so when I multiply those together, degrees Celsius cancels out. That gives me kilojoules. When I do that, 7.794 times 14.5 gives me 113 kilojoules. Okay, so that's the total heat change that happens in this calorimeter. Okay, now they want to know the heat of reaction for the combustion of a mole. Okay, in other words, 1 mole of the CH6N2. We just combusted 4 grams of it. Okay, so now we have to figure out how many moles that was. Okay, so 4.00 grams of the methyl hydrazine is CH6N2. And we change that to moles. So we got 12 plus 6 plus 28. It's going to give us, 46 grams in 1 mole. Okay, so we take the 4 divided by the 46. That gives us about 0.087 moles. Okay, and if we want to know kilojoules per mole, we just take this 113 kilojoules divided by 0.087 moles. And that's going to give us about, sorry, this is way down here, about 1,300 kilojoules per mole. Okay, so when we burn 1 mole of the hydrazine, we're going to get 1,300 kilojoules out. Okay, that's basically how that works. I think that's the last slide for the calorimetry stuff. Yes, it is. Okay, so we'll start Hess's law next time. And you're going to have to give me a second to end this video because this is taking so long. Alright, we will see you